All right, hello. We are going to be reviewing Unit 2 tonight, and this is going to be Unit 2A and 2B. So in the school year, we split them up into 2 units. We're going to sort of fuse them together into one unit today. The first part of Unit 2A was all about factoring, and we learned a bunch of different types of factoring, or reviewed a bunch, and we learned one more. But the first one you ever learned in your whole career was GCF. Remember, GCF stands for greatest common factor. So you want to look for numbers and letters that might be in common. So in this case, 9 goes into all 3 terms. We have an a squared that can go divide evenly into all 3 terms, and a single b, because even though both of these have a b squared, this one only has 1. Once you factor out a GCF, you then start a parenthesis and essentially divide every term by whatever your greatest common factor was. So that will leave us with a 4a squared b minus 3b plus 1, and that would be how you would take a GCF. The next type of factoring that we reviewed was dots. Stands for difference of 2 squares. So literally in the name, it's the subtraction of 2 perfect squares. And when you go to factor that, this is my favorite kind. You basically square root both terms. So the square root of x squared is x, the square root of 36 is 6, one gets a plus, one gets a minus, and it doesn't matter which one gets the plus and which one gets the minus, as long as they get one of each. Now, if the number comes first in a perfect square, then the number has to go first in the factor of that dots factoring. A to the 6th, you're essentially taking your exponents and cutting them in half. So we have a to the 3rd and a to the 3rd, plus and a minus. Then we started learning about grouping. Grouping is when you have maybe 4 or 6 terms. You want to group 2 at a time. If there's 6 terms, it could be 3 sets of 2 or 2 sets of 3, depending on the question. And what you want to do within the group, once you have them grouped together, the first 2 have an x in common, second 2 have a b in common. And what you want is these 2 common binomials, we want that to happen. If you don't get a common binomial there, then either you didn't take the full GCF out of your group, or maybe some rearranging needs to happen. But once you have these 2 factors match, you factor that out as if it's a common binomial factor, and whatever is in front of that becomes our other factor, other bubble, sometimes I call it. A common mistake is because they see x plus 2 square or x plus 2 twice, they think that they have to put an exponent on it. You do not put an exponent on it. So let's practice that one more time. My first group has a 2x in common, and 2x goes into each other. That factors out to be an x minus 1. Because there's a minus here, and I know that this needs to match this, I'm going to take out a negative b. So that will leave me with a positive x and a minus 1, and there my common binomial factor comes out once, and whatever's in front of those becomes my second factor. Another type of factoring that we reviewed was something called trinomial factoring when a is 1. Now that's a mouthful, so I usually call it AM factoring. AM factoring stands for what adds here that multiplies here. If you're stumped, there is a calculator hack that you could do. You could do 18 divided by x in your calculator. You go to your table of values and you can find your factors of 18. Obviously 6 and 3 make a 9, so that's the one we're going to go with. So what multiplies to 18 but adds to 9 would be 6 and 3, and then they need to combine to a negative 9, so they're both going to be minus minus. So same idea for number 2. Multiplies to 15, adds to 2 is going to be 5 and 3, but this time it needs to add to negative 2. So my rule of thumb is usually the bigger number takes the sign in the middle. So the middle number is negative, so the bigger number is going to be negative, and negative 5 plus 3 makes a negative 2. Now to make this a little bit more difficult, trinomials when a is greater than 1, the little tagline for this one, I call it triangle method. Some teachers call it the AC method. And the reason why they call it the AC method, not like air conditioning, but AC method, like the front number and the last number multiply together and you make this like magic number. That's why I call it triangle method, because it kind of looks like you just made a triangle. But now instead of multiplying to 15 adding to 11, it's multiplying to 30 but adds to an 11. So if you think of all your options that multiply to 30, 1 times 30, we have 2 times 15, we have 3 times 10, and we have 5 times 6. I want to pick the one that's going to make the 11. And so once you pick that option, what you want to do is you want to split the middle. And I kind of try to be strategic about it, because if I'm going to split 11 into a 5 and a 6, I know 6 goes nicely with 2, and I know 5 can go nicely with 15. Now, it doesn't really matter which order you put them down in, but sometimes I like to be a little bit more strategic, that I know when I do my grouping, it's going to like gel nicer together. So 2x, and then I'm left with an x plus 3. This has a 5 in common. Again, I'm left with that x plus 3. We just reviewed factor by grouping a couple of problems ago. These are in common, so that becomes my common factor, and then the GCFs become my other binomial factor. So if we practice that one more time, triangle method here, my magic number is a -6. Now that negative is important. So I need to think of things that multiply to a negative, but will add to a positive 5. And 6 is always one of those tricky numbers, because you're like, well, it could be 2 and 3, or it could be 1 and 6. In this case, because we're multiplying to a negative, that means signs have to be opposite. So we definitely have to go with 6 and 1. Now, if we're going to add to a positive 5, it's going to be a positive 6 and then a -1, because 6 minus 1 makes a 5. Group it, group it. -1 in common on the second half of this, so that my 2 common binomials match. And so my final result will be my common binomial and my original GCFs. All right. 2 more types of factoring that we learned in this unit. Factor completely isn't really a type of factoring. It's when more than one factoring presents itself, so that we are able to say that it is factored completely. So usually it's a GCF first. It's not always going to be, but I would say probably 85% of the time it's a GCF first, and then some other type of factoring. So in this case, this is definitely GCF. They have a 2 in common. And once I factor out that 2, I notice that it's dots that's left. So that's x plus 4, x minus 4. And actually, same kind of idea in number 2 here. We do have a GCF across the board of a 6 and an x. And when I sort of assess what I have left, because of that 2 in front of the x squared, that does tell me that I need to do some triangle method action here. So multiplies to a -2, but adds to a -1. I'm going to split the middle and make that a -2x plus 1x. Group it, just like we've been a couple times now. This is my GCF out front. These 2 have a common factor of 2x. These have a common factor of a 1. And so I can write my final answer of all 3 of my factors. 6x was my original GCF. X minus 1 was my common binomial, and then 2x plus 1 becomes my remaining binomial factor. Okay, dun dun dun. We got to the one that was brand new to everyone. Everyone has never learned this until you got to Algebra 2 this year, and that is SOAP. Essentially factoring 2 cubes, 2 perfect cubes. What you want to look for is something that you could essentially think of this as something to the 3rd power and something to the 3rd power. 2 times 2 times 2 is 8. So 2x cubed. That if I did 2 to the 3rd power, that would give me 8. X to the 3rd power would give me x cubed, obviously. 27 is 3 times 3 times 3. So 3 cubed is 27. But now that I have these sort of split like this, 2x is what we're going to represent as our A, and 3 is going to be represented by B. So if you look at the order, the reason why we call it SOAP is because if the original problem has a subtraction sign, it's same sign, opposite sign, always positive. Same sign, opposite sign, always positive. So this breaks down into a binomial times a trinomial. I sort of like to prep the space. So same sign, opposite sign, always positive. I put those in first because then I know where I need to fill in. The first binomial is the A and the B, just like I had it written here. Then it goes A squared. So 2x squared would actually be a 4x squared. A times B would be 2x times the 3 would make a 6x in the middle. And then the B squared, 3 squared is a 9. So let's practice that again. We have x to the 9th plus 64. I want to think of this as what to the 3rd power plus what to the 3rd power would make an x to the 9 and a 64. Well, x cubed is x to the 9th. And 4 to the 3rd power is 64. So here's my A, here's my B. I'm going to prep my space. Same sign, opposite sign, always positive. And then in order, it goes A, B, A squared, A times B, and then B squared. Okay, so that was factoring. Now we get into the solving aspect of things. So now what you'll notice is there's an equal sign involved in our setups. So we're going to have to use our methods of factoring for us to be able to solve these quadratic equations. So for the first one, I see GCF. Once I have it factored, I can T-chart. I set each factor equal to 0. And obviously, if I could do 3x equals 0 divided by 3, it's still going to be an answer of 0. But this one will equal -5. If your equation isn't already set equal to 0, obviously you want to get it equal to 0. Factor T-chart. So multiplies to 10 but adds to 9 would be 10 times 1 minus plus T-chart. And basically, if it's just one of these common factors like this without a number in front of the x, you can just switch the sign and get your two solutions. Now, if something is not factorable, like our next example, the quadratic formula, which is a formula that is provided on your reference sheet, so you don't have to have it memorized, even though most of you probably already do. You can use the quadratic formula to solve any quadratic, but remember it has to be a quadratic. So if this had an x to the 4th power, I can't use the quadratic formula. A quadratic only has an x squared. So essentially we want to get this in standard form, set equal to 0. And once we have it set equal to 0, we can find our A, our B, and our C and plug into our formula here. So x equals -b, but b is already negative. So we have a +4 plus or minus the square root of b squared minus 4 AC all over 2a. All right, so I substituted in our A, B, and C values. I am going to find what's called the discriminant, which is the number under the radical. I don't like to type the radical in with it because I never know if it's going to come out to be a negative or an irrational number, something like that. So I am just going to type it in exactly as I have it written on my paper and get my discriminant. We then would have to read the directions of the problem itself. Does it want simplest radical or does it want rounded to a certain decimal place? So I'm going to show you both options. If the question is asking simplest radical, then we need to take this 24 and break it down to be a perfect square multiplied by a non-perfect square. The square root of 4 is 2. And then I like to look at these three numbers. I call it checking my triangle. And if those three numbers, not including the radical, are divisible by something, then divide it by that something. So in this case, 4, 2, and 4 are all divisible by 2. So in simplest radical form, it would be 2 plus or minus 1. You don't have to write the 1 if you don't want to, divided by 2. That would be considered simplest radical form. Now, if it asked for in decimal form, I am a huge proponent of using alpha y equals. So alpha y equals, enter, type in 2 plus the square root of 6 over 2, get your first answer. So there's a little smudge on my screen. It looks like a negative, but it's not a negative. It's just a little smudge. My positive answer would be 2.22, whatever it told me to round to. And then you can go up and grab it and copy paste and just modify the plus sign to be a minus sign. And that would get you your second answer rounded to the nearest whatever it asked for. If a question does not say solve by any means, like the quadratic formula, and maybe it specifies solve by completing the square, completing the square is unique in the fact that this one actually doesn't want to equal to 0 first. This one, you actually want to move the constant to the other side. And because I'm cheesy, since it's called complete the square, I like to introduce a square and then I literally fill it, but some teachers just use a space and that's also fine. To fill the square, it's this formula. So you take b, the b value is the middle number. So 12 is going to be our b value. So if we take the middle number, cut it in half, and then square it, what I noticed, 12 cut in half is 6, 6 squared is 36. So I'm going to be putting a 36 on both sides of our equations. You do not want to get this one equal to 0. What you want to actually go ahead and do is factor the left-hand side and then add up the right-hand side. So -4 plus 36 is 32. This is multiplies the 36 and adds to 12 would be 6 and 6. These two factors should be the same because the whole point is to create a perfect square with them. I can write them as a single factor squared. From here, if I'm trying to solve for x, I square root both sides. Don't forget your plus or minus, because when you square root something squared, it creates two answers, plus or minus. Square root of 32, that's not a perfect square, so I have to break it apart. 16 times 2 is the biggest perfect square that goes into it. Square root of 16 is 4. And our last move would be to shift the 6 so that you can solve for x and isolate the variable. Then we moved on to curve sketching. So curve sketching, we talked about even and odd degreed functions, what their end behavior was, what is a 0, what is the y-intercept, minimums, maximums, increasing, decreasing, positive, negative, all that good stuff. So this one, I'm going to make an assumption here that if the y-axis is counting by 2s, I'm going to make the assumption that the x-axis is also counting by 2s. It doesn't really label it for me, so I'm just going out on a limb here. So the zeros are where it crosses or kisses the x-axis. So the zeros, that would be considered a kiss. And this would be a 0 because it's crossing the x-axis at 4. So my zeros would be at -2 and at 4. And technically, I would have 2 -2s because of that kiss happening at that spot. The y-intercept is where it crosses the y-axis. So that would be right here. This is our y-intercept. Minimums and maximums. So if I say, how high did the roller coaster go? In this case, the biggest, sort of highest point that it reaches in the window that I can see, it goes up to 4. If it doesn't say the coordinate of the minimum or maximum, then don't write it as a coordinate. If it just says what is the maximum or the relative maximum, this is a relative maximum. This is a relative minimum. That is the lowest it went. The lowest it went was 0. It didn't dip below it. So 0 is the relative minimum. It doesn't say coordinate, so I'm not writing a coordinate. End behavior. Well, I noticed that this end on the left is going up and this end on the right is going down. So as x values are going towards -infinity, that's this way towards the left. As x goes to the left, my y values actually go up. My graph is going towards positive infinity. But as my x values are getting bigger towards positive infinity to the right, my y values are actually decreasing. It's going down. My possible degree here, if we count our kisses and crosses, kisses count as a multiplicity of 2. My crosses count as a multiplicity of 1. So this is definitely a degree 3. I also knew that it was odd degreed because my ends are going opposites. Where is it increasing? Increasing. So if I think of this as a roller coaster, it's going down, up, down. So this middle section is where it's increasing. Now, intervals are always the x values only, and it is tempting to pick the y values. So if we are thinking about increasing in terms of x values, that is increasing from an x value of -2 to an x value of +2. Where is it decreasing? It's decreasing in these two pieces. Since this is going, I know it's going up, but remember we have to think of it in terms of x values. So from the left to a -2. So from -infinity to -2, then it increases, and then starting at 2, it goes to the right. I know it looks like it's going down, but it's going to the right, and we have to think of things in terms of x values, so towards positive infinity. Positive versus negative is as if I sort of chopped off the bottom half of this graph, and I had to write the interval of the entire portion that's above the x-axis. Now, positive is exactly what it means, positive. 0 is not considered positive or negative. It's like this neutral weird zone. So this first segment from -infinity to -2 is positive. At -2 itself, it's not positive or negative, hence why I'm using a parenthesis. Then it starts again at -2 and goes all the way to 4. This whole piece right there is positive. So from -2 to 4, it's positive. The only piece that's negative is from 4 down. So from 4, I shouldn't say down, over to positive infinity, that is where it is going to be negative, AKA below the x-axis. Even and odd function, this is kind of already spelled out for you. We've talked about even and odd a few times throughout the year. Even has to be symmetrical over the y-axis. So if I fold something perfectly over the y-axis and it folds right on top of itself, that's considered an even function. It has nothing to do with its degree. If I have to prove it algebraically, you plug in a -x for the function, and if you get the original back, then it's considered even. If it's odd, it has to be symmetrical with the origin. So that's the easy one that I think is the best to remember, because odd origin, OO. So if it's symmetrical through the origin here, then we have odd, it's an odd function. Again, not related to its degree in any way. To prove it algebraically, you plug in a -x, and if you get the negation of the original function back, it's considered odd. If you get some combo platter where some of it stayed the same, but other parts of it switched over and switched its sign, then it could potentially just be neither. All right, so we just have a handful of examples left, and we'll be done with this. So some extra problems. An open box is to be constructed from a square piece of sheet metal, removing squares of 6 inches from each corner and turning up the edges. So we have a square piece of sheet metal. I don't know the original dimensions. That's what we're going to try and figure out. But I'm going to be cutting squares from each of the corners that are 6 inches being cut away from each corner. So this is gone, this is gone, this is gone, this is gone. And what that allows me to do is sort of fold up the sides and create an open top box. But what we need to decide is what is the length of that little tab and what is the length of that little tab. So if the original piece of sheet metal I didn't know, we'll consider the original length X. So if the original length was X and then I cut 6 from this side and I cut 6 from this side, I am cutting a total of 12 inches off of this original piece of sheet metal. So that's X minus 12. And since the original piece of sheet metal was a square, then this is also X minus 12. So I'm creating this box that has a width of X minus 12 and a length of X minus 12. I need to figure out how tall it is. How tall it is if I took this flap and I folded it up, it would have a height of 6. So now I have my 3 dimensions. There's no lid, which isn't super important in this example because it is going to hold 294 cubic inches. 294 cubic inches is telling us a volume measurement. Volume is length times width times height. So I actually really don't care that there's no lid. So if the volume is 294, and it says length times width times height. That's 6 times x minus 12 times x minus 12. Algebraic solution only. So algebraic solution only means I'm not going to really use my calculator much. I need to solve this by hand. There's a couple different ways you can solve this one. There is an easy way and a difficult way. I'm going to show you the easiest way. The hardest way is if you took the time to FOIL it out, distribute the 6, get it equal to 0, use the quadratic formula. That's actually the hard way. The easy way is to notice that we have x minus 12 written twice. So you can write it as a single factor squared. Then divide both sides by the 6 and you get 49. And this might look semi-familiar from what we just reviewed with completing the square, because now we have a perfect square equal to a perfect square. I can square root both sides. Obviously the square root of 49 is 7, but because we're square rooting something squared, we get plus or minus 7, which allows us to set up two cases. X minus 12 equals positive 7, x minus 12 equals negative 7. Add the 12, add the 12. And I get two potential answers. But if you go back to the original problem, remember we were cutting and removing 6 inches from each corner. So a total of 12 inches. I can't cut 12 inches away from 5. So I'm going to reject that answer. So the original piece of sheet metal must have been 19 by 19 inches. Number 2, the area of a rectangle has one corner on the graph of 36 minus x squared. 36 minus x squared is a reflected parabola shifted up 36. So let me just draw a quick little sketch of what that looks like. So we would have a y-intercept of 36 and then a sad parabola from there. I'm not going to really care so much about the negative side, but I'm going to really focus on quadrant 1. So I have a rectangle that has one corner on this curve, another at the origin, a third on the positive y-axis, and a fourth on the positive x-axis. Now, I just drew a random rectangle following those directions, but I could really draw a rectangle in any shape or size. I could have done on the graph, on the line. I could have had a really tall, skinny rectangle. I could have had a really wide rectangle. Any of these rectangles are fair game. What we're trying to find is what is the biggest one I can fit under this curve. So if we are discussing area of a rectangle, that's length times width or base times height. Oh boy, there's a dog barking in the neighborhood, and that's never a good thing. And I'm so close to being done. Area is length times width. Since the bottom of this is on our x-axis, let's call that length x, because I don't know what it is. It's some magical x value. And since this is on the y-axis, let's call it some random length y. And it feels like I haven't really gotten far, because length times width is x and y, and I have 2 variables. It's really not helping me. But in the problem, I have this, that y equals 36 minus x squared. If I can set up an equation in terms of just one variable, I can now use my calculator to help me figure out the maximum or the largest area. So I'm going to head over to my calculator, and this whole equation is going in my y equals in my calculator. So I'm going to go over my y equals x times 36 minus x squared is going in my y equals screen. Now I am going to have to do some adjusting. So if this is 36 and this is representing our parabola here, 36 minus x squared, in theory, if I go to my table, by the time I get to 6, I shouldn't have any height left, because that's when I will hit the x-axis. So I'm going to modify and adjust my calculator's window. I'm going to cover this up now so I can scoot that up. I'm going to adjust my window in my calculator and have my x values go from 0 to 6. Now, if I only look from 0 to 6 in my x values, I notice that my y values hit this high point around 81-ish. So I'm going to go from 0 to 100 just to give me a little bit of wiggle room in there. So press the window. We're going to modify our window to show just like this, 0 to 6, 0 to 100. and then hit graph. Hopefully, if you adjusted it correctly, you see what I see. I need to find that maximum peak. So to find the maximum peak, I'm going to hit second trace, option number 4, left bound, hit enter as long as your blinky spider's to the left of the highest point. Right bound, hit enter once it's to the right, and then guess somewhere in the middle. It says round to the nearest thousandth for the X value. So I'm going to write the whole thing down just in case there was ever a part B to the question that asked what is the maximum. So 3.464, comma, 83.138. And my answer is what value of X? So my X value is 3.464. And last but not least is curve sketching. So part A says, what are the function's zeros counting its multiplicities? So the zeros are when I set the equation equal to 0. And what I notice is they have a common GCF of X squared. Once I take the X squared out, it is AM factoring. I'm going to kind of use some of the space here. So multiplies to 3, adds to a 2. So that should be minus, that's a minus sign, 1. And so my zeros, if I t-chart this, I get 0, -3, +1. But because this is an X squared, this is going to end up being a kiss with a multiplicity of 2. This was a cross, so that'll have a multiplicity of 1, and this will have a multiplicity of 1. My y-intercept is when X equals 0. So if I go back to the original problem and I plug 0 in for all the X's, 0 to the 4th power plus 2 times 0 to the 3rd power minus 3 times 0 squared, it's just going to literally come out to be 0. So my y-intercept is going to be 0. You probably could have guessed that if my x-intercept is also 0. So if I go over to my graph, I'm going to try and spread this out a little bit because otherwise it gets a little crunchy. So we have an x-intercept at 0, 0, which also happens to be our y-intercept. We have x equals 1. So that's like really close next to it. I'm going to skip a line and I'm going to label that a 1. And then my other solution is -3. So again, I'm going to skip, that's -1, that's -2. I'm going all the way out to here to represent -3. But before I can connect these zeros, I have to figure out what is our degree. Our degree is 4. It's the highest degree or exponent in the problem. And if it's degree 4 and there's no negative out front, so it's a positive even degreed function, my end behavior should be up, up. Meaning, as x goes to the left, my y values should go up. And as x goes to the right, my y values also should go up. So this should go up and this should go up. I have a kiss happening here. So if I'm crossing through -3, kissing at 0, then this is going to have to like swoop back down for me to be able to cross through 1. All right, that concludes Unit 2 review.